All right. So to prepare for the Virginia Tech math competition, which is, as I said, this Saturday, I thought it would be nice to do some more Virginia Tech math problems. So this problem, I think, was from their 2008. So Virginia Tech. So x, y, and z are positive integers. You want to solve 1 over x plus 1 over y plus 1 over z equals 1 over 2008. Show there are only finitely many solutions. So this is a really good problem as a practice for several reasons. One, as I said, it's from the same people who are writing the exam that you would be taking on Saturday. Two, it has a lot of really good features. What's the first thing, or one of the first things that comes to your mind when you look at this? The 2008. They actually thought of this problem back in 1993 and had to wait until 2008 before it was useful. No, right? When you see problems like this, for the most part, the year is a throwaway. It's just that someone's trying to have a little fun. They're writing a lot of these exams. Do you think 2008 really matters? If I changed one word, or a few words, if I changed the finitely to count how many solutions, do you think the 2008 would matter? Yes, but because they only want finitely many solutions, the 2008 shouldn't be that bad. So again, when you see problems like this, you want to start thinking, let's analyze. So one, analyze the year. So you should all know whether or not 2014 is prime. Okay? All right, I'll do that one. It's not. You should know the factorization of 2014. You should know the next prime may be after 2014. You should. No, you can do that one on your own, or go to Wolfram Alpha. Or do the Siva Verasthenes if you get bored in class. All right, so analyze the year, see if the year is important. Look for keywords. What do you think the most important word is? Any other candidates? Integers. And in fact, integers is part of a larger phrase. Positive integers. So I think the key words here would be positive integers, and I would say finitely. I can't remember if they actually said show or if they said prove. When you're doing these things, you should basically do as much of a proof as you need to. Okay? Why do you think they say positive integers and not just integers?
It's false.
Yeah. So usually if you tweak a condition, it is either very hard to prove or it's false. So if you tweak the positive, let's take x to be 2008 and y to be okay, and z equals okay. More generally, I would say take x to be 2008, y to be negative z. And so if you do something like that, you now have infinitely many solutions. You have a whole family of solutions. So the questions then becomes boring if you allow negative integers. It would only become interesting if you then asked how many solutions do you have, say, in a given region. If you assume that x, y, and z are between negative b and b, let b grow, how many solutions do you have? There are b cubed or 2b plus 1 cubed possibilities. Which fraction of those triples work? Something like that could become interesting. All right, so the next thing for this is there is one other number that's hidden in this problem. This one's a little bit harder to see, but there is a third number, or there's a second number. I guess we've only seen one number so far, the 1 over 2008. What else? 3. So find the numbers. 3 is hidden. So where is 3 hidden? Right. So do you think that this is true in general, or do you think that this is something special about x, y, and z? Well, here, let's just choose something at random involving x, y, and z. X plus y equals z. Solvable or not solvable in the integers? And let's even do positive integers. x squared plus y squared equals z squared. Solvable or not solvable in the positive integers? Okay, so I guess we should start. Let's do one more. X cubed plus y cubed equals z cubed. Not solvable. In fact, this is Fermat's last theorem. And in fact, this is a function of what the name of this course is. So the correct way when you abbreviate this course is with a lowercase l. So how many of you have taken abstract algebra? I've got to make sure my hand is down. So have you heard of Fermat's little theorem? The way you're supposed to abbreviate Fermat's little theorem is F little lt to distinguish it from Fermat's last theorem.
Does Fermat have an I theorem?
I don't know. To fit? That would be imaginary, which doesn't exist. So here you see that there is a huge change in complexity as we change the exponent. There are people who've looked at generalizations of Fermat's last theorem, and some people say this is not the right question to ask. Anybody know any other? Well, okay, so I mean, Fermat's theorem in general replaces the three, well, I'll leave the threes, replaces this with x to the n plus y to the n equals z to the n. But there are some people who say this is the wrong question to ask.
How many you need?
Yeah, how many you need? The sum of two squares is a square. What do you think this should have been? So you can then ask, well, what happened if we add a w? Can you write z cubed as the sum of 3 cubes? Can you write z to the fourth as the sum of 4 fourths? And there's a whole slew of questions you can ask. And again, what I like about problems like this is to use them as a springboard to talk about good mathematics. I will put some stuff about the Beal's conjecture on this. Another way to, in vain, try to win a lot of money. So let's go back to our problem. We've got 1 over x plus 1 over y plus 1 over z. Do we think that it's essential that we have 3 variables here? Do you think that there would only be finitely many solutions if there were 4? Or 5 or 6? When you have a problem like this, how could you build intuition? What could you try to do? So this is a more general problem. This is the problem of we want to solve the reciprocal of 1 over x1 plus 1 over x2 plus 1 over xn equals some number. And we want to know, are there finitely many solutions to that? What could we try to do? The 2 case. What else could we try to do? The 1 case. In fact, this sits in the general framework of induction, right? I know it's been taking normally about now 30 minutes to get to induction. Today we're getting to induction a little bit faster than normal. When in doubt, think induction. And you'll try to look at simpler cases. Try to build up your intuition. Now the problem is, if you try to build this up by induction, you may have to generalize the problem a little bit. How should I view this problem? I should view this as, I want to know if the sum of the reciprocals of n integers equals. So it could be the reciprocal of another integer. It could be something a little bit more general than that, though. What else could it be? Instead of the reciprocal of an integer, it might be the reciprocal of a. Well, reciprocal of a real number is a little bit harder. Anything would work. It could be the reciprocal of a rational. And so when we're trying to break things into smaller cases and then build up, if I fix the value of z and subtract it over from this side, it's unlikely it's going to be the reciprocal of an integer, but it will be the reciprocal of a rational. So in terms of how you would attack a problem like this, I think you want to look at trying to solve not equals 1 over 2008, but actually trying to do something more general. And this is another common trick they do in puzzles and contests. They give you a specific instance to try to make you think of a specific result. Whereas if you make things a little bit more general, the proof becomes easier. Can I do an abstract algebra aside? All right. So we say a number is algebraic if it solves a polynomial with integer coefficients. Else it's transcendental. So numbers like the square root of 2, I, these are all algebraic. It's harder, but pi and e are transcendental. Okay? I'm sorry?
It's extremely hard.
No, it's not extremely hard. No. It's tedious. It's not hard. There's a difference. So here's the theorem. Either e plus pi or e times pi is transcendental. We actually believe both of them are transcendental. We can only show that at least one of them is transcendental. Does anybody have any idea of something that might be useful in attacking e plus pi and e times pi? E to the I pi equals -1. Does that seem like it should play a role in the analysis here? We want something about e and pi. Here is a way to connect them. Don't need that at all. The general statement is if you have two transcendental numbers, either their sum or their product is transcendental. Probably both. It's a general statement. And what happens is the sum of two algebraic numbers is algebraic. The product of two algebraic numbers is algebraic. So algebraic plus algebraic equals algebraic. Algebraic times algebraic equals algebraic. And so now, if e plus pi and e times pi are both algebraic, look at e plus pi squared minus e times pi with a 4. And when the dust settles, you get e minus pi squared. It also turns out that the square root of an algebraic number is algebraic. And if you think about it, if you think about the polynomial, if you replace all the x's with x squareds, you can get the square root. So now we know e minus pi squared is algebraic. Its square root e minus pi is algebraic. So if I look at e plus pi plus e minus pi, that's going to equal 2e, and that would be algebraic. And then you divide by 2 and you get e is algebraic. So a lot of times, you can get obsessed with things that don't matter. And a lot of times it's actually easier to convert the problem to a more general framework and say, really, I don't care about being the reciprocal of an integer. I just care about the sum being a rational number, a fixed rational number. Okay? So again, these are just general problem-solving advices, general ways of looking at things like this. Okay. So what I want to do now is let's try to prove by induction that if we have the sum of a finite number of reciprocals, it's always going to be finitely many solutions. So the claim, if we fix a rational number that's greater than 0 and n a positive integer, only finitely many solutions to 1 over x1 plus 1 over xn equals 1 over r. So there will only be finitely many solutions. So what would be the base case? N equals 1. The proof, I think, yeah, you laugh, you chuckle, right? You're trying to solve 1 over x1 equals 1 over r. This is not a difficult equation to solve. Right? Can you prove that there are only finitely many solutions to this? Yes. If r is an integer, there's a solution. If r is not an integer, there's no solution. The base case is not that hard. So then the problem becomes, what if you now look at the general case? And that's where we have to do a little bit of work. All right, so general case. So we can assume that there are only finitely many solutions if we look at one variable less. Just to go through the details, let's look at the case of 1 over x plus 1 over y equals 1 over r. And if you want for definiteness, we'll do 2008. We'll do the year that they wanted. What can you tell me about x and y? What are the possibilities for my solutions? They're positive integers, but do you know anything else? Yes. You didn't raise your hands up. Yes.
They have to be greater than 2008.
Good. Why do they have to be greater than 2008?
Because, so if they're less than 2000, if one of them was less than 2008, then the other one would, that's bigger than one over 2008.
Good. So we know clearly 2008 has to be less than x and y. What else do we know?
They can't be bigger than, wait, yeah, they can't be bigger than 4016. Or they can. Wait, never mind.
Okay, you're on the right track. You're close.
That bounding.
You're close.
Not fitting the word right.
You're very close. Yes?
The product has to be divisible by 2008.
That may be true, but that's not going to be helpful.
One has to be less than 4016.
One has to be less. One is less than 4016. Because if they were both greater than 4016, then their sum could not be as large as 2008.
Less than or equal to, right?
Less than or equal. Less than or equal to, yes. Or we'll do it like that. That's much cleaner than rephrasing and putting it in, squeezing it in. So now we know that. I'm sorry?
Oh, okay, I see.
So now they can't be too small, and one of them can't be too large. So in problems like this, introduce order. For problems like this, it frequently helps to introduce an order. Do you want x to be the largest or the smallest? Smallest. Does it matter? No. So x less than or equal to y. And when z comes into play, it'll be less than or equal to z. So we now have a situation like this. So if x is the smallest, we know x has to be less than 4017. So now we would get 2008 less than or equal to x less than or equal to 4016. So we have a range. Okay, so now that we have this range for x, what can we do? We can get a range for y. How are we going to get a range for y? It's going to be better than just a range for y. We've got 1 over x plus 1 over y equals 1 over r. Well, we're doing r equals 2008. So 1 over y equals 1 over 2008 minus 1 over x. So once you've told us what x is, there's at most one y. Given x, at most one y works. Well, if at most one y works, and there's only finite many x that we can try, as only finitely many x, only finitely many pairs. And this is another good example of how a lot of problems like this work. If you can handle frequently the first non-trivial case, you often see the brushstrokes of the general theory. And so now by doing this case, by doing the case of two terms in great detail, hopefully the case of three terms isn't so bad. We'll order them x is less than or equal to y is less than or equal to z. For a fixed value of x, there's going to be a fixed range that x can live in. And now we have 1 over y plus 1 over z is 1 over a rational number. And we know by induction there's only finitely many solutions. So again, you don't necessarily have to go through and do this problem by induction. If you want to, by all means, you're welcome to. And you can prove a much stronger statement. This is not necessarily a bad thing to do, can impress the judges. We will prove more. We will prove that there are only finitely many solutions to, and then this is a special case. So, the final step, here, we'll choose x less than or equal to y less than or equal to z. bounded range of x, each x only a finite number of pairs of yz, finite times finite equals finite. Okay? So this is the first time we've really done an induction in full detail, I think, in a while, especially so early in a class day. Any questions about this? You could cross multiply, and you could set this up as just a equation of polynomials. And you're asking, how often does this polynomial have solutions in the positive integers? This is a huge field in number theory, trying to figure out which polynomials have solutions. And then the next thing is, once you know they have solutions, what do you want to do next? How many? And once you know how many there are, find them. Where are they? What we've done is we don't really know where the solutions are. We have an algorithm that would allow us to find it. Our algorithm is essentially try all possibilities. But we have an algorithm. Question?
So now we're saying we have a bounded range of x.
Right.
So essentially we're saying, since we showed it from the 2 case.
Exactly, by induction.
Okay.
So in general, we would have n terms here. And so the first one, the smallest one, is in a bounded range. And then by induction, we have one fewer terms. That has a finite number of solutions. Therefore, we have a finite number of solutions. So it was very important in terms of doing the induction that we do not view this as the reciprocal of an integer. Because when we're trying to do it as a reciprocal of an integer, we're in trouble. What is a question you might be curious about right now?
Are there any solutions?
Yeah, are there any solutions? Right. Oh, there is a solution?
Oh, wait, sorry.
Oh, I was wondering if anybody checked and saw, is there a solution?
To this question.
Yeah.
Yes.
Okay, what's the solution?
0, 0, 2008.
No!
X, Y, and Z equals 6,024.
So in something like this, we can just take all of them to be equal, and then you get 1 over 3x equals 2008. But wait a minute, is 2008 a multiple of 3? No.
We do 1 over 3 times.
I'm sorry?
It's 3 over 3
It's
times
3 over
2008.
All right, so what are you telling me my solution is?
It's 3 over X,
So tell me what to take for x, y, and z.
6,024.
6,024? For all of them?
Yeah.
Okay. Okay. Oh, that's right, because it's 3 over x, not x over 3. Good, perfect. And then when you take that, you get 3 over 3 times 2008, which is 1 over 2008. So do you consider this a satisfying solution? No. If you're a real mathematician, this is not a satisfying solution, right? What would you like to impose?
But they're all different.
That they're all different, right? You would want to find, can you solve this in the positive integers where x does not equal y does not equal z, where there are 3 distinct numbers? That's much harder. It then prevents you from doing trivial things like this. In a lot of problems in number theory, the main contribution is actually frequently from the trivial number of solutions, the solutions of the trivial form, and then you just try to show that the other ones don't contribute fully or contribute less. Okay, so time to move on to a new problem. So the next topic that was requested was logic theory. So there are 4 riddles that I've sent you to think about. My favorite to do is the egg drop riddle, because that's the one I don't know how to do and I haven't thought about. So I saw at least one person nodding their head. Who wants to do the egg drop riddle? All right, so should we do the egg drop riddle?
Yes.
Yes. Wow, you all know how to vote. Excellent. All right, how many of you have heard the egg drop riddle before? So wait, nobody's heard the egg drop riddle before? Anybody want to try it? It's the egg drop riddle. You have 2 eggs building with maybe n equals 100 floors. Each egg safe to drop from floors less than or equal to D. If safe, can drop, again, no damage. So you can drop an egg as many times as you want from any of the first D floors. And every time you drop it, it doesn't shatter. You pick it up, you drop it again, does not shatter. There's no cumulative damage. You can do this indefinitely. However, what do you think happens if you drop from D plus 1 or higher? It breaks immediately. Okay, so no matter what floor you choose, if it's greater than D, it breaks immediately. And the goal, find D in as few drops as possible. All right, so continuing the theme, what do you think the most important words are in this problem? 2. We have 2 eggs. What else? I'm sorry? 100 or whatever the number of floors is. Good. What else? I'm sorry? Few, right? Trying to do it in as few drops as possible. Can anybody give me an algorithm that will find a D? I don't care how bad it is.
Start dropping the egg on the first floor when it breaks.
Right. Start at 1 drop. If okay, increase by 1 repeat. This will work. Now the problem can become interesting if you assume a distribution of where the egg is likely, where the floor is likely to be. If all the floors are equally likely to be the special floor, on average, how long is this going to take? About 50 drops. Do you think the egg is equally likely to drop to shatter at all places? Probably not. But you don't know, this could be a mathematical egg. This could be an egg that the physicists have done something with their liquid nitrogen. I know there was...
It could just be an egg, and if you drop it from a single point,
could be a regular egg. How many of you have ever played hacky sack? Hacky sack was illegal in my high school. It was illegal because you could be playing hacky sack and the ball could go out the window and you could dive for it and you could hurt yourself. We were a 1-floor high school. I don't mind saying hacky sack is illegal, but we always felt that this was a stretch to eliminate hacky sack. There was, I know, something in summer science or the summer science programs a few years ago where there was an egg dropping contest, I think, where people were trying to design contraptions to drop eggs as safely as possible. All right, so this is a strategy that will work. If all the floors are equally likely, it's going to take on average about 50 drops. Can anybody think of a better algorithm? Or before we try to find a better algorithm, what should we be doing?
You just like take one at some arbitrarily high floor, and if it breaks, then you know that D is less than that.
Right, so the problem is, so let's say we drop it at floor 50. All right, so if we drop it at floor 50, if it breaks, we know it's now somewhere between 0 and 50, or between 1 and 50. If it doesn't break, then we know it's somewhere between 50 and 100. That's why we have 2 eggs. And so unfortunately, in a situation like this, one of the things that's important to notice is what is the worst possible runtime? What is the average runtime? So for a problem like this right now, we might only be caring about the worst possible runtime. So I know there's a lot of hands up, so let's just try to get everything on one stage first. So if you drop it on 50 and it doesn't break, where will you drop it on the next time?
Then you can just like start at 1 and keep working your way up.
Well, okay, if it breaks at 50, you have to go from 1 and you have to move up.
Right.
If it doesn't break at 50, where do you go next?
So you can just start going to 50, or you can go to 75.
So you can go to 75. So in some kind, you're cutting things in half. Yes?
Don't we only have 2 eggs?
You only have 2 eggs. But if it doesn't shatter when you drop it from 50, now you know it's somewhere between 51 and 100.
If you then drop it 75 and it breaks and you don't know D and now you don't have any eggs left.
No, the egg didn't break when you dropped it from 50. That's why you moved on to 75.
Otherwise you go down. You still have.
So if the egg breaks,
At 75.
no, if it breaks at 50, then you go with the second egg up from 1.
Right.
If it doesn't break at 50, you go up to 75. And then if it breaks,
Okay,
you have
so
1 egg left. You have 1 egg left.
Yeah, I was gonna say, you just use one of your eggs like a search egg, and like bounce the range for your
Okay, so we're basically using 1 egg to try to get a rough sense. And unfortunately, as soon as we get 1 failure, we then... It's pronounced freshman, but you can... So, again, greater good, okay? And you can always get more. But here's the question. Before we go further, there are no perspectives here today, right? 'Cause we've had a couple of perspectives. I know there's parents here, but you're not thinking of going back to school, are you? Okay. We do have 2 parents. No, sorry. So there is one question about this. So we have binary search. That's what's really going on here. This is one of my favorite algorithms in mathematics. For those of you who ever have to do things with little kids, a great version of this is I can guess your birthday in 10 yes/no questions. And you basically say, is your birthday on the following date? If I'm wrong, you have to tell me earlier or later in the year. And so you just do a binary search. Were you born?
Get away with not remembering kids' birthdays.
One of many ways. I say, were you born on July 1st? And if they say yes, shocking. If not, then you go, and you know which way to go. Do you need 10 questions to get someone's birthday? No, 2 to the 10 is 1024. Give yourself a little bit of leeway in case you make a little bit of a mistake. The kids are not going to be so concerned with the 10. All right. Binary search is really powerful. Is binary search the best thing to do here? Why might binary search be bad?
We have 2 eggs and it won't take it into the fact that we have this other one.
I'm sorry?
If we just move up by like 2 at a time, then we might have to check all 50.
Right, so the problem with the binary search is here's 1, here's 100, here's roughly 50. If we do a binary search, we could be stuck going all the way up floor by floor by floor over here. Now the binary search covers an enormous amount of ground. That's a huge plus. But the disadvantage of the binary search is that if it fails, we now have to cover here. We have 2 competing influences. And it's not concern for the egg. That's not one of the competing influences. What should we do?
So you can instead use the first one to chunk it up and then search that chunk. And
So where, you got to tell me where.
no, so go by 10s.
By
First
tens.
one goes by 10s, and then
All right, so if you go by tens, it'll take you how long?
at most 20.
At most 20. So if we go by tens, not to scale, that could take us as much as 20 times. Maybe it's 19, maybe it's 20, I don't care. Something like that, because worst case is we go 10, 20, 30, 40, 50, 60, 70, 80, 90. And then after 90, what do we start to do? It seems like this is not necessarily the most efficient. Because once you get up to 90, you should be able to do something better. What would you do once you're at 90? So you could do binaries, but then that's again coming back to this problem. So for something like this, it's sometimes a good idea to do small cases and get a sense of what's the best you can do and use that to build your intuition. Or another thing for a problem like this is instead of doing a binary search where we do it at the halfway point, where should we do it? Yes, the auth point. Right?
Are we worried about finding D in the worst case?
So again, for a problem like this, I would say let's be worried about the worst case for D rather than the expected value of D. And again, depending on what your metric is, different things will be very important. So let's do worst possibility, how long would it take? I think that there should be some natural point r. So we split it into here, and then that could take us r minus 1 steps. And then over here, we would have, so we'll call it maybe r times n. Well, r will be a percentage. And if we have something like this, we could try to analyze how long would it take. So the first suggestion was to take r equals a half. The second suggestion was to take r equals a tenth. Right? What would be the right thing to take? If we take r equals a third, how long could it take us?
36.
Yeah, it could take us on the order of 30 something to do it. So if we take r equals a third, that could be a long time. If we take r equals a fourth, on the order of 25. You know, I don't care so much within a 1 or 2. So, you know, we've already got something where we do things by tens, which is already going to be on the order of 20. And so, you know, if we're not getting something that's that good, we're in trouble. The other question, of course, is when you have something like this, hopefully whatever method you use, you can then just use that method again on the smaller set. Because if we made it here, it's essentially like we've started all over again with just a smaller number. So if we tried 6, well, if 6 broke, then there's only about 16 things to do. That's a little bit better than 19. And so maybe something like 1/6. So the one question is, maybe some kind of strategy like that might be a little bit better.
What about 7? That gets us really close to 100. Like 7 is almost equal by.
So one question is, there might be better numbers maybe depending on this number.
Yeah.
Possibly. Okay, any other thoughts before we continue? So again, I'm not convinced that this is the best strategy. I think the binary search is going to be a little bit better than moving up like this. And so, worst case scenario, if we have n things, it could take basically like, if we do it into 6s, n over 6 steps. Right? So, say we break into m pieces from n. So our ratio is m over n. That would be how high up we're going. So the number of steps, worst case, is what? Is m. And so now we have to figure out how do we want to view that m. We can view that as r times n, what our ratio is. So if we take our ratio to be, we want maybe r to be 1/6. We suggest maybe 1/6 or 1/7 could be a good thing to try. If we do that, then the worst case is the first egg breaks. We now have to check 1/6 times n, or about 16 things. So if it breaks, it would be 1/6 times n. What if it doesn't break? Now what we're left with is we were left with something of size 5/6 n. Right? And worst case, how long would it take us to figure out something here? What would that be? So if we have n things, and we're splitting it up 1/6 of the way up, so this is n over 6. The worst case is if that first egg breaks, and now we have to do step by step by step by step by step. And that would be about n over 6. Now, it's like we're playing the game all over again. It didn't break. We now have a segment of size 5/6 n. We now check up, we go up 1/6 of that. Worst case is it breaks. So I think these are the two cases. If the first egg breaks, it'll take us this many steps, or maybe a +1. If the first egg doesn't break, it'll take us something like this. Yes?
Why can't we change our step size after the first step?
We could. And that would make things even more complicated, is if we change the step size depending on how much we have left. So this is assuming the same step size every single time, and we're just iterating this whole procedure. And so if we did that, if n equals 100, this side is going to be about 100 over 6, so this is going to be around 16. This would be around 500 over 36. I'm sorry? So we take 36, if we multiply by 15, 6 times 5 is 30, 15, 16, 17, 18, 3, 6, 0, 4, 5, 40. So this would be less than, say, 16 when we add 1. Okay? So if we just do it like this, we actually have a bit of a savings over doing it every 10th. So this is just to try to get a sense of what do we have to do to actually beat this idea of checking every 10th. What makes this problem so challenging is we don't have to do the same thing every single time. Have I done an algebra mistake, or is the algebra correct? Okay. Not quite sure what's going on outside, but. All right, so the question is, do you think that the best thing to do is always the same thing each time? Or do you think that depending on what you have, you want to make your drops in different places? I think that can clearly come into play when you have a small number of levels at your disposal. So the more we can narrow down the possibilities. So what should we be doing for a problem like this that we have not done? Induction, investigate small cases, build your intuition. You know, it's great that we have some idea of what the answer could be. It's great that we have some idea of things that would work, but we should try some small cases and get a sense of what is the best we can do in different configurations and try to go from that to see what might be the best algorithm. So let's take n equals 1. All right, not a challenge. I feel like this is Yom Kippur. No, Rosh Hashanah? Rosh Hashanah. I feel like it's Rosh Hashanah. No, it's more of Rosh Hashanah. Tequila. Okay, so n equals 2. What do we do for n equals 2?
You pick one.
Doesn't matter. If you drop it from the first floor and it breaks, what does d equal? D equals 1 if it breaks. If it doesn't break, d equals 2. If you drop it from the second floor and it breaks, oh, it does matter. So drop it from the first. All right, so if we drop it from the first, we'll be fine.
Can D be 0 or does it
D can't be 0, but D could be 1. It could break from the first floor.
It doesn't really say that it has to break though. So could you have a case where it doesn't break?
True. Okay, you're right. So then for a problem like this, we should be careful as to whether or not the egg must break at some point.
But then it's still, you can still just drop it from either one and then drop it from the other one.
No, but it makes a difference. If the egg doesn't have to break, if you drop it from the first floor and it doesn't break, if it has to break, you know it breaks from the second floor.
Yeah.
So, but if it doesn't have to break, you would still have to drop it from the second floor to figure out that it's safe on the second floor. You wouldn't know that yet. So you're absolutely right that this is a good subtle point as to whether or not it has to break or not. So I'm checking to see how they phrase the problem. All right, so I have it phrased as one of the floors is the highest floor and it can be dropped from without breaking. So there is a highest safe floor. Unfortunately, that highest safe floor could be the top. So I think the way it's phrased, you cannot assume that there is some floor where it will break from.
How would you know that the top floor is the highest safe floor?
Well, if you keep trying every single thing and you finally get to the top floor and it doesn't break, then you know the top floor is. So unfortunately, in this case, if we drop from the first, we still have to drop it from the second if it doesn't shatter. So this could take 2 steps. Could take 2 steps. Not a given that must break. And that's the problem, is that it might be possible to keep dropping it from higher and higher floors. All right, what if we now try n equals 3? What do we want to do? We're probably going to run out of time too. I got about a minute left. So what would we do if we take n equals 3? 1, 2, 3. Drop it from the second. If we drop it from the second, it'll take at most 2. Drop from second at most 2. So right now the pattern is not clear. We need to go much higher up to really get a sense of what's going on. So n equals 4. One, two. So if we drop it from the second, if it breaks, we know it's either 1 or 2. If it doesn't break, it's either 3 or 4. And then that will take us 3 drops. So if we drop it from the second, this will be 3 drops. If we drop it from the third floor, if it breaks, we know it's 1 or 2. That could take us 3 drops. And then the other ones will be worse. Yes?
If you jump from the third and it breaks, can't you just check for the second?
Oh, okay, good. So let's see, you drop it from the third, it breaks. You drop it from the second, and if
that breaks, then you know it's the first floor. If it doesn't break,
no, why do you know it's the first floor?
Could not break it.
It could break everywhere.
It could break everywhere.
Yeah, so can you have D equals 0?
Oh, D equals 1, I think. Oh, D. Oh, I see what you're saying. Yes, D could be 0. We don't necessarily know that it has to break from some point. I mean, we don't know that there has to be a safe floor. That's the problem. All right, so it's now 11:50, so we've got to stop here. So if people want, we can continue working on this problem next time in terms of what is the best strategy.